So today I'm going to be presenting about a project of mine called Data Morph, and particularly why you have to be careful with summary statistics. So we kind of went over a little bit about this bio, so I will skip over and just mention again that I'm a software engineer at Bloomberg in New York City, and I'm the author of Hands-on Data Analysis with Pandas. So summary statistics aren't enough to describe your data. So if we look at these three data sets, I'm pretty sure we would all agree that they are very clearly different. However, if we just look at the summary statistics, then we would not be able to say that. So here you can see that these three images, right? So we have the Python logo on the left, some slanted lines in the middle, and a heart on the right. They all have the exact same mean in the x variable, the same mean in the y variable, the same standard deviations for x and y, and the same Pearson correlation coefficient. So in order to distinguish these on a numerical level, one thing we could do is look a little farther into the distribution, and this can be done with what are called moments. So the first moment is going to be the center of the mass of the distribution, and that is going to be the mean, which we already know was the same. And the second moment would then be the variance, which is again the same as we saw before, that the standard deviation was the same. You'll notice that these numbers will be a little different, and that's because these are central moments, so it removes the effect of the translation. So, but once we get to the third moment, right, so that is then the skewness of the distribution. We now see differences in the x variable and differences in the y variable for all three of these data sets. So if we add the marginal distributions as histograms to these plots, we can again clearly see visually these are definitely different distributions, even just looking at x or just looking at y. And in this case, I've replaced the third moment with skewness, which again was the name for it. That is a measure of the asymmetry of the distribution. And then the kurtosis, which is the fourth moment, and that is a measure of the weight in the tails. Right, so for example, if we, actually you probably can't see my mouse, but on the heart one, if you look at the distribution of the y variable, so the one that's going up and down, you'll see that all the way on the top part of it, there's a really, really high peak in the histogram. And then, so that is a measure of the weight in the tails, right? And so that one has a large kurtosis for that reason. Okay, so when we went to look at those moments, right, we were then able to see some differences between those data sets. And sometimes even looking the third and the fourth won't be enough, and you'll have to go further. There are many more moments, but that's way beyond the scope of this. So by looking so granularly into just x and just y, we obviously then have lost the measure of how x and y correlate, how they move together. And so here I brought back the visual with the correlation coefficient. So here it's indicating that there's no correlation between anything. So that's not really a big issue in this example, but we know that the Pearson correlation coefficient is measuring linear correlation. So if we just look at that number and don't visualize it, then we also can't be sure that even if something indicates that there is a correlation, that it is actually linear. And so an example of this is from Anscombe's quartet. So this is a data set that was constructed in 1973 to illustrate this particular concept. And if you look at the first and the third, those are definitely linear, right? But you'll notice that for the second and the fourth, which are most definitely nonlinear, they have 0.82 correlation coefficient, indicating that there would be a linear, in quotes, distribution, like that, as a strong correlation there. And that is definitely not the case. So visualization is a key part of any data analysis. And there's a 2020 paper called Hypothesis is a Liability. And the researchers there argued that simply approaching a data set with a hypothesis may limit the thoroughness to which the data is explored. So I want to walk you through the experiment that they ran. So they took students in a statistical data analysis course, and then they split them into two groups. So one group of those students was given a task of exploring a data set. So basically they were just given a data set on number of steps per day, BMI, and then male, female. And then they were asked to just see if they found anything in the data. And then the other group was given the 3 hypotheses you see on the screen, and they were asked to test if each of those was statistically significant. So they were guided in what they were supposed to be doing. And so this was what the data set looked like, right? So here you can see that this was most definitely not real data. And the researchers took a gorilla shape, and then they just sampled some points along the outline of the shape, and then made up the sex variable that they have there. And what's interesting about this experiment is that they found that the students that were given the task of testing those hypotheses were 5 times less likely to notice that the data that they were looking at was a gorilla, right? So it's key, the idea here is that just because they were given that task, they didn't fully analyze the data, and they missed the fact that the data was actually a gorilla. So how do we encourage students and practitioners alike to be more thorough in how they conduct their analyses? So I would argue that part of this is creating more memorable teaching aids. And so going a little bit back in time, in 2017, we have researchers in Autodesk created what was called the Datasaurus Dozen. So they're building upon that idea of Anscombe's quartet, where they have those 5 summary statistics staying constant. They took the dinosaur, which is at the top, and then they turned it into the 12 shapes at the bottom, all of which share those same 5 summary statistics. And they also added animation, which makes this particularly more impactful than just looking at the Anscombe's quartet or even the previous slide. So you can see here that every shape that we encounter in the transition from that dinosaur to the circle and then back shares those same summary statistics to 2 decimal points, right? So you can see here that it's not just the dinosaur and the circle that share those summary statistics, but the infinite number of arrangements of points we encounter along the way that also share those summary statistics. So this should make you wonder, if you're just giving summary statistics, you don't really know at all much about the data. And then this leads now to a new problem, is people now conflate this with there being some particular property about that dinosaur, that datasaurus, that allows this transformation to happen. And that's simply not true. So because there's no way that, well, like before that, what I'm gonna, my project that I'm gonna show to you, there was no easy way for people to do this on their arbitrary data set. So either they went and they found the dinosaur and then they showed that, or they showed Anscombe's quartet, but there was no way for people to convince themselves that this was just an innate property of summary statistics. And again, repetition is something that is key to learning. So maybe you see the Datasaurus Dozen and you see Anscombe's quartet, but maybe you need more examples to convince yourself, or also just to make something stick in a teaching environment. And so that's why I built Data Morph. So Data Morph is an educational tool, and it addresses the limitations from those previous methods that I mentioned. So for one, it's an installable Python package. So this means it can be used without having to hack on research code, which is the process of how I made it. And it gives you animated results automatically. So rather than having to, again, hack at that data or to somehow add animation on top of Anscombe's quartet, you can use Data Morph directly. You basically say your inputs, your outputs, and it generates an animation with your custom data, right? And it's possible to use additional data sets. So not just that dinosaur that I was showing, but I have, and I'll discuss these further later, built-in data sets that are additional ones, like the Python logo that we saw earlier. And also you can use this with your own arbitrary data. So this allows people to experiment with their own data. So in the case of like educational tool, you can think about perhaps using a school logo or something, a design that a student creates, and then they can work on converting that into target shapes. And they can also make their own target shapes. So the target shape, which I'll talk about later, could be something like they want to turn their school logo into a heart. And all of this now means that there's no limit on the number of examples that can be created to illustrate this concept. So here's what Data Morph looks like. This is converting the Python logo into a heart. You can see again that those 5 summary statistics have been preserved to 2 decimal places, and the points are moving throughout from the Python logo to the heart and then back. And this is something that is provided by Data Morph without you having to do any extra configuration. So I want to walk you through a little bit how that works. So at a high level, we, in the first line, install Data Morph from Python's PyPI, so we use pip. And then that adds this executable here, so then you can just call Data Morph and you can pass your starting shape, which was the Python logo, and then the target shape, which is the heart, so what it was going to be morphed into. And under the hood behind that, it can be boiled down to just this little bit of Python code here. And I want to talk a little bit about how the algorithms behind this work. So the first thing is we have to select our starting data set. So there's this data loader class inside Data Morph, and that has this method load dataset, and you can just pass in either the name of a built-in one or your CSV if you want to use a custom shape. So what's different about, or what allows this morphing process to happen is this dataset class that is part of Data Morph. So this is not a data frame. It stores its data in a data frame, but it is so much more than that. So it has, in particular, these bounds, which are shown on the screen. So the innermost set of bounds are called the data bounds, and that is the limit of how far in the X direction and how far in the Y direction the data is going. So that's basically the tightest box that can fit around the data without excluding any points. And then the middle one are the morph bounds. So that tells the algorithm how far it's allowed to push the points outside, away from the original shape, before it's not allowed to move them anymore. And then the final one, the outermost one, is called the plot bounds. And that tells Data Morph which frame of reference it should be using when doing the plots. So this makes sure that we don't have any visual shaking, and it's a constant frame. And so all 3 of these are used for, as I mentioned, the plot obviously for the visualization part, and the morph bounds and the data bounds are used for the algorithm, both for figuring out where should the shape that this is going to be turned into be placed, which I'll get to it in a little bit, and then also how the algorithm is allowed to move the points. So in the current release, I have these data sets already built in. And like I said, you can use a CSV file to use arbitrary data sets. So once that data set is created, we can then create the shape that it will be turned into. So the shapes don't exist without the data set because they're calculated from the data set. So there's this shape factory, which is going to be bound to the data set. And then we will call this generate shape method, and that will perform the calculations to make the heart, for example, specific to the Python logo. So here's an example of how that works. So you can see in the top row, I'm making shapes based on the Python logo. And in the bottom row, I'm making them based on the music data set. So you notice that the music data set is taller than it is wide, whereas the Python logo is symmetrical. So in the case of the Python logo, you notice that the heart seems to cover more of it, whereas it doesn't go, it's not completely stretched on the music one, and that's on purpose, right? So we don't want distortion of the shapes. So for example, if the star if somehow was really tall for some reason or really wide, it wouldn't look as good. So these shapes are basically, so there's heuristics built into the shape. So given the data set, they can determine where to place themselves on the XY plane. And you can see that even in the case of the heart, the Python logo and the music shape, the heart is centered at a different spot. And it's also scaled differently. And that's all done with statistics from the data set itself or from those bounds that we were just discussing. And so in the current release, I have these shapes available. So you notice that these are, again, more shapes than were initially provided in the research. And the initial research was basically just a bunch of if-else statements. So it was basically, if your starting with a dinosaur and you want to turn into a circle, then the circle is centered at this exact point. So this is all now drop in and like you can create your own shape or you can create your own data set and everything will still work with Data Morph. So I'll talk a little bit about high level about how the shapes work. So I mentioned before, because before it was if else statements. So to move away from that, the algorithm that's moving the points around only ever needs to know, given a point it wants to move, how far will moving it to a certain spot make it from the values, right? And so that's the distance method. So there's this abstract class, the shape class, that defines kind of the interface, like what needs to happen for it to be a shape. So it needs to have a plot method for documentation purposes, and then a distance method so that it can be used in the algorithm. And then the next level are kind of the building blocks, if you will. So a circle is kind of a special case where there's a formula to calculate the distance from the formula for the circle. But the line collection in the middle and then the point collection on the right, those are just collections of points and lines. And so basically the distance is then just the minimum distance to any of the lines or the minimum distance to any of the points, which then means if you want to create a new shape that is made up of lines or a new shape made up of points, you don't even need to figure out how to do the distance, right? Because it's already done for you. You just need to figure out how you want to place it in the XY plane. And then it becomes a little bit of a math puzzle. Like how do you create a heart? And a fun fact about that heart shape is it's actually a trigonometric equation. Okay, so now that we have the data set and the target shape, we can actually perform the morphing. And so that is done with the data morpher class. So it's instantiated, and then it has this morph method where it takes the starting data set and the target shape, and then it does the full process. So the process, the algorithm that's being used is called simulated annealing. And here I have some examples of that algorithm going for a few iterations. So a point is selected at random, and that's when you see it glow blue. And it's going to be moved a small random amount to a new spot, and that's when it turns red. But it will only be moved to a spot where it's going to preserve the summary statistics. So this is mostly untouched from the original Autodesk research. And you'll notice if you look at certain iterations that sometimes when the point goes from blue to red, it's actually moving away from the shape. And this is just part of how simulated annealing works. So it's a randomized optimization algorithm. And so sometimes you need to allow moving in a suboptimal direction because this actually helps avoid getting stuck in a local optima. And the likelihood that you do this decreases over time. So this is the temperature variable of the simulated annealing process. So you can see here I have 3 examples of duration, so how many iterations we're going to run the algorithm for. And in all 3 cases, the temperature decays over time, but it lasts the full amount, starting from the max all the way to the min. So one thing I added on top of the initial algorithm was to also do a similar type of thing like the temperature, but for how fast the points move over time. So to get this visual effect, you can allow the points to move fast, like move farther initially, and then as you get towards the end of the number of iterations, you decrease the amount that they're allowed to move over time. And so you notice when an animation starts out, the points seem to scurry away very fast, and then they start slowing down as we get towards the target shape. And I think that adds a nice visual effect than it being constant speed. And again, like the temperature, it has a similar decay, but in this case, we don't want to drop it to 0 because if we did, then nothing would happen and that would just be wastes of those iterations. Because it's very visual, you do want to see some level of movement. Okay, now I want to talk a little bit about the limitations of the way this currently works and then some areas for future work. So the first thing are what I call bald spots. So perhaps when I was describing this initially, you had some picture in your head, like the one on the left. So given the dinosaur converting into the heart, everything's nicely placed, there's no clumps. But what ends up happening is on the right. So I've outlined what the heart target was, and then on top of it, what actually happened. And you can see, like, for example, in the bottom where the pieces come together, there is a bit of clumping. And there's also that bit on the top right where there is nothing there, right? And if you look at the dinosaur in that same spot, those points are pretty far away from that. And so nothing in there in the algorithm right now encourages trying to move those points that far away. So they end up getting clumped. So the next thing is the direction of the morphing. So I mentioned before that we start from a data set and then we morph into a shape. And then obviously if we play that animation in reverse, then we effectively move from the shape to the data set. But right now there's no way to go from a shape to a shape. So for example, the heart to a diamond, or data set to data set. So dinosaur to panda, for example. And these each come with their own set of challenges for the shape to shape, right? So the shapes use the data set to determine where to place themselves. So something needs to stand in for that initial bit. And then that bald spot problem would also be an issue. And on the data set to data set, that's even more complicated because what does the distance metric look like in that case? How do you determine which shape gets scaled and positioned on top of the other one, right? And then the bald spot problem also comes into play. So the next one is speed. The algorithm, as I mentioned before, is largely untouched from the initial research. Potentially parts of it could be vectorized, but it is kind of challenging because it's a very iterative algorithm. You move one point a tiny bit, that changes the summary statistics ever so slightly, not enough to fail that check of 2 decimal places or whatever you set it to, but it is changing ever so slightly. So you need to, it would be a challenge to work in batches on that. I do have someone who submitted some pull requests. I did a sprint on this at EuroPython earlier this year, and someone did do some effort to speed up as far as reducing the number of calculations. So there are some things that can be done. The next thing is that the scale of the data affects how many iterations it takes to morph to the shape that you want, like visually saying that it has been enough. So if I take that dinosaur, which is the one in the middle, and I scale it to half size on the left, then that takes about 25,000 iterations. The one on the left takes about 50,000 for the one in the middle. And if I scale it up double size to the one on the right, that takes almost 78,000 iterations. So you can see it's the exact same shape, right? It just takes more iterations to move because we're moving the points a little amount each time. And it's not a matter of just saying, well, allow them to move more, because then that actually causes the algorithm to get stuck. So there's a simple trick, like if you're realizing this is taking too many iterations, you can scale it down, like the one all the way on the left. But this would also be something I would like to tackle to avoid the need to do that. And next I have convergence. So particularly this kind of ties in with the previous one, right? Because if the data has a larger scale, one of the tricks you can do again is scale down. But sometimes you say run for 50,000 iterations, and then it finishes and you realize, oh, like I needed another 25,000, and then you have to run it all again. And if you have small values, running it for 50,000 may mean you have those 25,000 at the end where points are just dancing around and nothing's actually happening. And so again, you might remake the animation just to shrink that amount. So I would like to, in the future, have a way to have some sort of early stopping test, so testing for convergence, and then allowing that number of iterations to just be the maximum. So at that point you stop, but hopefully you've converged before then. Okay, so I'll talk a little bit about the lessons I learned and challenges faced when I was doing this. So the first thing is that repeating research is hard. I started, as I mentioned, with the Autodesk researcher's code. And my first step was just to recreate what they presented in their paper, which was converting that dinosaur, the Datasaurus, into a circle. And I was trying to figure out exactly what was going on in their code. And particularly the issue is that they had their research code and then they probably attempted to clean things up, move things around. And so whatever they presented on the GitHub, which is where I got it, they had things that were clearly unused, variables that were never actually referenced, functions that weren't used, limited no code documentation in most cases, some strange naming for variables. And so it was very much a reverse engineering task. So it took me about 4 hours just to get the exact example that they presented working on my machine. And then from there, I wanted to get this to work for a panda-shaped data set because I wanted to use this in my pandas workshop. And I created an image of a panda, and then I reworked it to have similar summary statistics to that dinosaur so that I can kind of see what the magic value, magic numbers in their code actually meant. And I had some of the similar problems to the previous slide, except this now I also needed to decode what those hard-coded values meant, because in many cases it was actually some statistic of the data that they just weren't being clear about what it was. And so it took me almost 2 days to get this to work. And then once I got it working and I was like, oh, this is going to be a fun little thing to put in my slides, I then got to thinking about how it would be nice to have as an educational tool for something that could be used like in an introductory statistics course or in a course where people are learning coding and maybe a touch of statistics as well. So I decided to turn this into a package. And so here I had a whole bunch more problems, right? Because I had to pay for the technical debt that the researchers incurred. So I had to clean up all those unused variables, functions, rename things so that they were, quality names, add documentation, refactor the code base, which was like 1 or 2 files into a properly structured Python package. I wanted to be very thorough with having documentation for everything. So I also made a pre-commit hook so that any code that I was committing to the repository had to pass a check that it had doc strings written in the NumPy doc style. And this actually led to me becoming a core developer for NumPy doc because I sent that to them and they included it upstream. So then I also had to figure out a lot of the things that you take for granted when you use an open source project is that someone at some point in time had to figure out all these things for themselves, hosting some project that they were working on. So how do you build and host the documentation public without having your company do it? How do you create a robust test suite when you have nothing there first? I think I rewrote it a couple times just because once I would finish, I would have, it would be great if it worked this way. But it was a good exercise to really think about how to structure those things. And the final 2 things were just figuring out how do you even publish to PyPI? How do you publish to Conda Forge? And what can you automate with GitHub Actions and how to actually do that? And so this whole thing took about 2 months to get that first release. And it was largely because I was going on a podcast and I wanted to talk about this. So if it weren't for that, it probably would have taken 4 months or more. And just a side note here, there were a couple cases where I bumped into where I was, I guess, getting a little frustrated that things weren't working by using the documentation from other tools. And when you're new to something, your instinct is kind of to think that you are doing something wrong. But in both of these cases, the docs were actually, or the references I was using, either one, were actually incorrect. And so just kind of keep an open mind that that is also a possibility. So here I have some resources that I found helpful when I was going through this. You can find the slides on my website right down here. So remember, summary statistics aren't enough to describe your data. You need to use visualization, but don't just use one single plot, as that doesn't give you the full story. So here I have the information on how you can try out Data Morph. You can install from PyPI or Conda. The docs are linked to there, as well as the repo. Again, the slides are on my website. Here are the references to the papers that I discussed. And thank you. You can scan that QR code and it's a feedback form for me to see what you thought of this talk, but feel free to connect on what you see here. I have my website, GitHub, Twitter, and LinkedIn. And thank you. I'll take any questions now.
Yeah, we have a few questions in the live ODAC chat if you want to take a look at them.
Would you mind reading them?
Sure. Just 1 second. So Do you have any practical use case of this model?
Yeah, as I mentioned a couple times, right, it's a teaching tool. So this could be used in, for example, high school classes where they're just starting to learn code and how to approach data. I've had a few teachers discuss with me how they're going to use it in the classrooms, right? So they could work on more of a design exercise where they create their data and then actually go through the process of transforming it into a variety of shapes and then comment on why certain shapes work better than others, because it actually has to do with how things are being structured. If they want more of a math focus, they can work on creating a new target shape or designing those heuristics. How do we actually work with properties of the data to make these transformations work? And in the docs, I do have suggestions for how to use Data Morph in the classroom.
Thank you. One more question. Can the image be unmorphed once morphed?
So that's kind of just playing the animation in reverse, right? Which, so you can have the you can direct Data Morph to do only forward, which would be just the morph, or by default it does morph and then unmorph. So when we saw the Python logo, it went Python logo, heart, back to Python logo.
One last question that we have in chat. In the algorithm, does the preservation apply for only the first two moments, or can it be extended to higher order moments or other kind of summary statistics?
So right now, we're only using the 2 moments. We've also, someone was working on adding the median, and it also does work for the median. So this is a question where other people can come and contribute. We can discuss adding those other moments and how that works. Yeah, so like I said, I haven't explored that particular piece, but it does become a bit of an optimization. The more things that you tried to hold constant, probably the harder it is to move that. But that's, yeah, something I do want to explore in the future.